Hello and welcome to this presentation of the BGP Vortex. This work has been presented as part of the USENIX Security Conference 2025 in Seattle, and it is a joint project between me, Felix Stöger, and my co-authors Henry Birge-Lee, Giacomo Giuliari, Jordi Subira-Nieto, and Adrian Perrig. As part of this project, we shake at the foundations of BGP route convergence. We identified that the assumptions made currently no longer hold on BGP convergence, and we turn these insights into a concrete and very powerful attack, which can potentially flood the internet with hundreds, if not thousands, of BGP route updates per second. But let's not get ahead of ourselves, and let's instead look first into the issues of routing inconsistencies and routing instabilities. If we were to not have routing consistency, meaning some part of the network sees a different state than another part of the network, it could happen that data plane traffic is sent along a certain route, which is actually suffering from a link failure because this information, which is localized, has not been propagated globally yet towards the sender. So until the sender is made aware of it and switches over to the backup path, all the data plane traffic will go over a broken link and thus essentially somewhere along the lines be dropped. Now, if we were to look at routing stability or other instability, this can cause increased route churn, it can induce increased router load, and it might also constitute as a kind of a denial of service attack if an adversary does do this fluctuation maliciously. So here, as you can see, even just a single router fluctuating a certain amount of, just 3 routes, can multiply and cause an increased load across the entire network because there are many routers which have to react to this. However, as you can see here, the adversary has to continuously fluctuate these, or the router has to continuously fluctuate its routes, which means if this was done as part of a denial of service attack, the adversary would have to continuously perform these fluctuations. However, a more sinister way of doing route oscillations, which has been believed until now to not be possible in the current internet, is to induce infinite route oscillations, meaning that a set of autonomous systems is somehow triggered with a constant number of route updates to then oscillate routes infinitely. And unfortunately, we were able to induce such a setting, which is what we call a BGP Vortex, by an adversary which only has to send 3 well-formed BGP route updates. But to better understand this, let's step back even more and let's look at the Border Gateway Protocol. It is the backbone of the internet, and it is a distributed hop-by-hop route dissemination protocol, in which networks, based on local incentives, such as monetary ones, decide with which neighbors they want to share routing information with. Since this is a distributed protocol, we have to ask ourselves the question, does this even converge? And luckily, this was shown in 2001 by Gao and Rexford in their seminal work, where they state in simplified terms that a BGP system converges if ASs prefer routes from customers over those received by peers or providers. This statement encodes a critical assumption, namely that ASs prefer routes from customers over those by peers or providers. Let's look at these business relationships for a minute. A customer-provider relationship operates such that a customer pays money to the provider, which in turn forwards BGP routes to the customer, and furthermore allows transit. So the customer pays the provider money in order to send data plane traffic up through the provider into the entire internet. Now, crucially, since every byte of traffic, according to some function, costs money for the customer to route through the provider, so the customer will be very careful to not redistribute these routes to others' networks from which they don't earn any money. So concretely here, the customer would not announce this route from the provider 1 all the way to provider 2, because otherwise provider 2 could exploit this and essentially route for free, versus the customer would have to pay extra. Instead, these routes would not be announced. A second business relationship is the settlement-free peering relationship, or just peering, in which networks agree to not bill each other for data sent across interconnects. And since none of these networks make any money from routing to and from each other, they will, if they receive a route which costs them money to use, for example from a provider, they will not re-announce this to their neighbors. However, routes from customers, where they themselves will make money to route through them, will certainly be announced to their peers. Now, this is relatively abstract, but it can be concretized in this simple table. This simple table says that all advertisements for an AS that are received from a customer will be re-announced to all the other customers, peers, and providers, versus all the advertisements received from peers will only be redistributed to other customers because only through that they can make money. And lastly, all announcements sent from from providers will also only be announced to customers, so they can recuperate the costs that it costs them to route through their provider. And critically, of course, because they make the most money from the customer, make no money from the peers, and even have to pay money to their providers, when they have multiple routes available, they will always choose customer routes over peer routes over provider routes. This is essentially what this statement here says, that this is the preference according to which AS is routed, and it's been considered to be economically logical. However, we found that these assumptions no longer hold in the current internet due to extensive traffic engineering capabilities which are exposed by providers to their customers. What are we talking about here? We're talking about a feature called BGP Communities, which was announced as part of RFC 1997. It is an extra piece of information which can be included into the route advertisement for enhanced traffic engineering purposes. And the two capabilities that we use, one of which is a standard capability and one of which is custom, so it means it's not defined in a standard, but it is still very widely used, are the local preference lowering community, which allows a customer to reduce routes preferences below those of peers. So essentially, the provider will prefer peer routes over this specific customer route if it is tagged with this specific BGP community. And secondly, a kind of blacklisting community, which is the do not forward route to specific AS community, where thus the customer can tag the providers to which this route advertisement should not be redistributed to. Let's visualize the behavior of the first property, or the first BGP community, which is the local preference lowering community. Here, initially, let's say the customer announces a certain route for an IP prefix P to the provider 1, which will in turn, because it's a customer route, announce it to its peer, which is provider 2. Now, provider 2 will receive the same route, however, it will receive it with the local preference lowering community, which, based on my explanation before, causes the provider 2 to deprioritize this direct route compared to the route that has been received through the peer. So although provider 2 would have a direct route, it would not use it and it would instead route through provider 1. Right. And this is all the groundwork that we need on BGP communities. And with that, we can now transition to the concrete BGP Vortex attack. Right. So what is a BGP Vortex? Basically, a BGP Vortex is a little subtopology as part of the bigger internet, which consists of 3 benign peers and 1 malicious customer. You can see the topology on the right-hand side. So you have 3 well-behaving ASs and 1 misbehaving adversarial AS, which is a customer to all 3 of them. And all the 3 ASs, all the 3 peers support both the local preference lowering community and the do not forward route to specific AS community. And that only adversarial capabilities we require is that the adversary controls a BGP speaker in an AS that is a customer to all 3 of them, and that it is able to send legitimate and well-formed BGP updates. So we do not require any hijacking, any malformed packets, anything like this. All of this is BGP conform, and all of this is well-formed. Now, how does the concrete attack work? The attack, as you will see, consists of essentially 2 steps. In a first step, the adversary will seed its malicious advertisement to all the 3 other providers. And then in a second step, these providers will all by themselves start to oscillate the availability of this route. And thus, in a circular fashion, will create a vortex, thus BGP Vortex. So let's begin with the adversary announcing the first route advertisement to AS2. First, it will include the lower preference community, and secondly, it will disallow AS2 to forward this specific advertisement towards AS4. So AS4 will never learn from AS2 about this specific route. It will do the same for AS3. However, AS3 will be barred from sending it to AS2. and AS4 will be barred from sending this specific advertisement to AS3. So you see we have induced a cyclicity or a directionality. In this case, we've chosen clockwise direction. Now, without loss of generality, let's consider AS2 to be the next AS, which starts by re-announcing. AS2 can only re-announce it to AS3 based on the no peer 4 community. And AS3 will now compare its local route, which is the direct one, and the one it's received via AS2. The route via AS2 is more preferred because the local direct route has been tagged with the lower preference community. So AS3 will replace its current preference with the new preference. However, this new route has been received by a peer, and critically, peer routes are not redistributed to other peers. So AS3 will not re-announce this route to AS4. Instead, AS4 will then go ahead and announce its route towards AS2 only per the no peer 3 community. And AS2 will again do the same local comparison. We'll see that this indirect route via AS4 is actually more preferred due to the lowering community. And in turn, it will switch over to using this new route. Thus, it will invalidate and withdraw the old direct route. However, it will not re-advertise this route to AS3 because this route is a peer-received route, so it will not be sent to AS3. Now AS3 has no longer access to its most preferred route, so it has to fall back to its backup route. And this backup, less preferred route can be re-advertised to AS4 because it has been received from a customer, which is exactly what it does right now. And maybe you can already see the cyclicity going on because now AS4 has a new most preferred route, which in turn causes it to withdraw the currently announced route from AS2. AS2 has no other option than to fall back to its less preferred route, which will then be re-announced to AS3, and the cycle continues. Thus, you see that they are now stuck in indefinite oscillations. This is already bad enough because we've already now trapped 3 ASs in a continuous circulation of BGP route updates. However, this is not everything because due to how the internet is designed, it's essentially a hop-by-hop route dissemination protocol. So a large number of these BGP route updates will actually be propagated outwards into the entire internet, causing potentially hotspots where certain parts of the internet receive many more routes, or just in general flood a wide part of the internet with BGP route updates. How many and how prevalent this really is what we are presenting now in the measurement section. How prevalent are BGP vortices in the internet? Our analysis started by us taking the Kaido topology, which gives us a graph topology of AS relationships and how they are connected with each other. And then we augment or we extend this information with prior work by Birge-Lee et al. In 2019, which has conveniently already identified out of the 30 largest ASs, which of them support the 2 relevant communities. So now we have the AS relationship graph where 30 ASs are tagged whether or not they have this community enabled or not. And then all we have to do is to find these peering triangles among these 30 networks. And what we found is truly astonishing because we found that out of these 30 ASs, 21 of which are actually supporting both of the vulnerable BGP communities. And out of those 21, 20 of which actually are contained in at least one peering triangle. And not just one, but in the median, they're actually contained within 58 BGP vortices. And in total, this leads to 340 viable BGP vortices among these 20 ASs alone. And these ASs, since they're incredibly privileged in where they sit in the internet, remember they're the largest providers that we have, they're a customer cone, so the set of ASs which are somehow reachable through customer provider links is enormous, with over 96% of the internet being covered by these BGP vortices among the 20 ASs that we've identified. And if we were to consider all these ASs in the customer cone, in the median, if we were to trigger all these BGP vortices at once, they would receive 801 BGP route updates per single oscillation of a BGP vortex in the median. Now, how often does such a BGP vortex oscillate? We did some experiments, as you will see in a few seconds, And these experiments concluded that the periodicity is between 6.6 oscillations per second or even up to 40 periods or oscillations per second. In total, this could lead to between 5,000 and 32,000 BGP route updates per second to be received in the median by an AS in a customer cone. Right, so lastly, we're looking into the experiment section where we investigate the impact that a single BGP vertex can have on route convergence and data plane availability. Firstly, we asked ourselves whether the routers are actually practically vulnerable or whether they have maybe some protection built in. And we found that if we were to construct BGP vortices using combinations of three very widely used BGP implementations, firstly, the Cisco virtual router iOS XR 9000, and the very widely used open source implementations FRR and Bird, we found that all these routers are susceptible with different fluctuation speeds. The fastest fluctuation or circulation speed is with Bird, and the slowest one is with FRR. Now, that we know that that widely used BGP route implementations are actually vulnerable, we investigated what the impact of a BGP vertex is on data plane convergence. What we did is that we instantiated a BGP vortex and we included two ASs. So the BGP vortex consists of Bird routers, so the fast fluctuating ones. And we have an upstream AS, which runs FRR, and a bystander AS that also runs FRR. Now what we did is that we start a BGP vortex with different numbers of prefixes fluctuating inside of it. And we measure the time it takes from the upstream announcing its route and the bystander AS receiving and installing the new route in its routing table. And what we found is that we can delay it by almost 40 seconds in the worst case. But even if we don't consider the worst case, you can see there is a very distinctive rise. And we can, even in this simple toy example consisting of just 6 ASs, we can delay data plane convergence significantly compared to almost instantaneous convergence without the BGP vortex being activated. Now, in the data plane outage experiment, we're extending this topology further with what we call a downstream AS, which has a primary path through the bystander and the BGP vortex, and a backup path directly to the upstream AS. And what we want to identify is that if we were to send data plane traffic through the more preferred route and there is a network outage, how long would it take for this information to propagate and thus cause the downstream to switch over to its backup route? Essentially, how long is there a data plane outage? And what we found is that it's corroborating with our control plane experiment. And we find that the data plane outage can also last 30 plus seconds with a very distinct upwards trend in the number of routes that are oscillating within the BGP vortex. Right, so let's look into mitigations against BGP vortices. In the paper, we first propose temporary mitigations, which are supposed to, or partial mitigations, which are supposed to alleviate the immediate impact of a BGP vortex without tackling the root cause of the BGP vortex. In the paper, we also discuss alternative internet architectures that are likely to be immune against the BGP vortex as a whole, such as path-aware internet architectures like the Scion Future Internet. However, as part of the paper, we also give a very concrete mitigation against the BGP vortex, which I'd like to present right now. Namely, the insight that we are exploiting is that currently in the internet, you can easily use BGP communities that violate the fundamental GAO-Rexford routing assumption or GAO-Rexford routing model. Concretely, the inversion between customer preference and peer preference due to the lower preference lowering community is what we exploit. So our idea is that operators should pay very close attention to disallow BGP communities that violate these GAO-Rexford conditions. And in the paper, we also give a concrete rundown of how we analyzed these two concrete BGP communities. To visualize the rationale here, essentially the local preference lowering community allows the customer to reduce the preference of concrete individual routes. Now, as long as the reduced preference is still higher than that of a peer, everything is fine. So even this, where a lower preference is very close to that of a peer, is totally fine, as long as the preference is still strictly greater than that of a peer. Now, however, This is no longer permissible because a customer route is not allowed to have lower preference than a peer route, since it would otherwise, again, violate the GAO regs for routing assumption. Correct. Right. So let's conclude. What are BGP vortices? They are induced state of persistent route instability among 3 benign ASs. And a BGP vortex can be triggered using only 3 BGP route updates. And a single BGP vortex, or even worse, several BGP vortices, can generate thousands of BGP route updates per second. And we found that 20 out of the 30 largest ASs are in fact susceptible to BGP vortices, which means that over or around 96% of the entire ASs in the internet are within a customer cone of at least one BGP vortex. And this clearly indicates that the long-standing assumption on BGP stability does not hold, and possibly there are other interesting cases that have not been considered before that allow violations of the fundamental assumptions made by the BGP convergence proofs that we have today. Thank you for your attention. I'd be happy to receive any questions you might have via the email address on the top right-hand corner. And with that, thank you so much for listening.